Alright, so for our next problem, we're going to be talking about the Maxwell construction. So the Maxwell construction is represented by this graph over here, and it's similar to this graph that I've shown you earlier. Basically this is one of the generic cubic expression plots at a specific temperature, so, just like this one is at a specific temperature. But where this one has just a flat line in the middle, this one has curves. So, this one is similar to the ones that we plotted, up here that had the curve down and then the curve up. And we basically want to use this Maxwell construction to plot this solid black line on our plot that we made. So, what the Maxwell construction says is that, the point right here is the same as the point right here, and this point right here is that point. And this line is drawn, at this height, where the area under this part of the curve and the area under this part of the curve are equal. So that's where this line is drawn. That's how they determined where this line is drawn according to the Maxwell construction. So we can use integrals to find the areas under the curves, set them equal, and then we should be able to plot this solid black line. So what integrals are we going to be doing? So we're going to take the integral of the pressure minus the calculated pressure. So that's like this distance here, from this point to that point, and from that point to that point. So to do that, and you might ask, like, what are these points? Well, these are going to be the volume roots that we found in one of the previous videos. So using this cubic V, so for example, at a pressure of 1 times 10 to the 7th and a temperature of 600 Kelvin, these are our 3 roots. So we're going to use those 3 roots as like the limits of integration. So we're going to take the integration here, and then integration here, and then we're going to subtract these two, and set them equal, find when the areas are equal, and then use that to plot our black line. Alright, so next we're going to want to start defining our function to calculate the integrals, or to calculate the areas. So we're going to define, we'll call this function the areas, and we're going to want to input the pressure and the temperature, because we're going to need to call this cubic V equation, or function, and that has a pressure and temperature that needs input. Alright, so then within this function we're going to find our integral. And for our integral, we're just going to need to input a volume. Because we're going to input, the roots from this equation. But first we need to define what the integral is. So we're going to use Wolfram alpha to calculate our integral. So if you go to Wolfram alpha, and then we can type integrate. Alright. So then, let's see. Alright, so then we want to integrate, a pressure minus this calculated pressure right here. So we'll type that in. So it'll be minus R times the gas constant times temperature divided by volume minus B minus A divided by V, or volume, plus epsilon times beta times volume plus sigma times beta, and then close out all these parentheses, and then we're going to want to do this with respect to V. Alright, so if we enter that in here, it'll calculate the integral for us. Alright, so it's calculated our integral, and so this is what we'll type in as our integral. So let's put that back up here. Or here, we can split screen this as well, so that we can see it. Alright, So our integral, I don't want to confuse that, so we're gonna I'll just call it into. It's going to be equal to, so A. Alright, so we're going to want giant parentheses around this entire numerator. Well, we're going to want parentheses around this entire fraction, and then minus this out here, so we'll write that so we don't forget. Gas constant times temperature times NP dot log of B minus V. Alright, and then we need to be careful within these logs. These need to be the absolute values, because you can't have a real, logarithm of a negative value. And we know for a fact that V is going to be equal than B, or that V is going to be bigger than B, because B is the excluded volume, the volume of the molecules, where, V is like the whole volume. So we need to make sure that we put NP dot absolute of that in there. Alright. So those parentheses seem to match up. Alright. So we'll have big parentheses within here. So that's for this whole first term. And then we're going to want another set of parentheses for the numerator. And then that's going to be divided by our denominator. So we might as well type in our denominator right now. That's easy. So B times E minus S. So epsilon minus sigma. Okay, so then for our numerator. Okay, so we're going to have some parentheses around each term just to make sure they all stay separate. So we're going to have A. So we're going to have A times NP dot log of B times S plus V. And then we'll subtract that. Another set of parentheses, and these will be A times P dot, oh, we need to make sure these are log 10s, because Python defaults to a natural log, not a log base 10. Alright. So then, NP dot log 10 of E epsilon times B plus the volume, right? And then that will be plus our last term, which is going to be B times the pressure times epsilon minus sigma times the volume. Alright, so I think I've typed all that in. Okay, so it's now yelling at me because we haven't defined E and S yet, and A and B. So, but we can do that pretty easily. We've done it up here multiple times before, so I'm just going to copy this code that calls our ABAS function, put that up there, and then yes, those error messages should go away. Alright, so now we're going to want to return this integral, so we'll return that. Alright, so that's that for that function. So next we're going to need to actually call this function without no function, and we're going to call it to put in these roots from the cubic V function. So first we're going to need to call the cubic V function. So we're going to unpack the array that it gives us as V1, V2, and V3. So if we're looking over here at this plot, we've got V1, V2, and V3. Right. So then that is going to be equal to cubic V of the pressure and the temperature. Okay. Now we're going to want to use this integral function to find this area and that area. So we can call this the left area and not the right area. So let's do that. We can go, so left is equal to, so remember we're going to want to take the integral at this point minus the integral at that point. So this will be the integral of v2 minus the integral of v1. So left is equal to the integral of v1, or v2 minus the integral of v1. And then similar for the right area. So the right area is going to be the integral of v3 minus the integral of v2. And then we're going to want the function to return these values. So we're going to have return left, comma, right. And then shift enter. And so there we have our function that is going to calculate the areas for us. Alright, so I've just realized I made a mistake. So remember how I said that over here we were going to need to use log 10 instead of just log, because when you just type log, Python assumes that you mean the natural log. Well, I forgot to read over here, Wolfram Alpha also assumes that just a log is a natural logarithm. So instead of log base 10, should just be log. Alright, so now we should be good to go. Alright, so the next thing we're going to want to do is we're going to want to find where these two areas are equal to 0. So we're going to be doing that using the root function that I've showed you how to use, in previous videos. And so we're going to need to import that. So from scipy.optimize, we're going to import root. Alright, we'll enter that in. Alright. So basically what we're going to be doing is we're going to have it iterate through a bunch of different pressures, because we're going to know, we're going to know where the volume values are, because we'll get those from our cubic V function. And then we're going to know what we're going to have the areas function calculate these integrals, and for different values of P, and then we're going to have another function that's going to find the difference between these two, or I guess really the addition between those two, because one of them is going to be negative and the other positive. And so this one plus this one we want to equal 0, because then they will be, same magnitude. So, so let's do that. So we're going to define, so the function that's going to add up these areas. So areas difference, I guess, although one's going to be negative, so we're going to be adding them together anyway, but it's fine. And then we're going to want to have a vector in there, and the vector is what's the root function is going to be iterated through. So it needs to be a vector because the root function is set up so that it can iterate through multiple different things, so it'll always look for a vector. But that vector is just going to be the pressure in our case. It's going to be a one value thing, so we'll have the pressure is equal to the vector, and it's going to be equal to the first value of the vector because there's only one value. And then we'll have the additional argument of temperature, because we're really only finding it for one temperature curve at the moment, not any temperature. So we'll have that. And then we need to find these areas. So we just need to call this function areas that we've made. So we're going to have the left area and the right area. It's going to be equal to the areas function of the pressure and the temperature. So this pressure is going to be iterated through because it was from this vector, and then the temperature will remain constant because we're only looking for it on one temperature curve. And then we're going to want to return left plus right. Because one will be negative, one will be positive, so when those are equal to 0, which is what the root solver solves for, then that would be where our roots are. So, shift enter on that. Forgot a colon up here. Alright. So then, alright, let's see what our root does. So, use the root function. First we need to input which function we're minimizing. So, minimizing the area's diff function. Next, we're going to want to input the vector that it's going to look for. And again, this vector is just going to have, one pressure in it. So we're going to input our initial guess for the pressure. So this will change as it iterates through different values, but we need to provide it, the starting value to start with. So let's go with 1 e to the 4th Pascal. And then we also need to input a temperature, but we don't want to put it inside the vector here because that's not what it's iterating through. So we can do that with args. So this will be the additional arguments that the root will input, and so we'll need a temperature. So let's say we put a temperature of 373.15 Kelvin. So let's just try that out, see what happens. Alright, so you'll see we've got a bunch of stuff that outputs. What we're really looking for is this array X at the end. And so that right there is our pressure that's at this line. It's also the vapor pressure of our substance, so that's cool. So let's isolate this. So dot X. Alright, and then you'll notice it's still an array, but it's a one value array, so we're just going to pull it out of the array because we don't need a single value inside of an array. Alright, and we just have the vapor pressure and the pressure at which these two areas are equal. Alright, so the next thing we're going to want to do is work on getting the values that we're going to plot, because eventually we're going to want to make, this solid black curve with that on this plot up here. So, first we can just copy this plot down here and make a new plot. But we're going to call this fig 2, just so it doesn't get confused with the other figure we made. Alright? Alright, so we have the same plot here. We're going to want to make that curve right there. On here. It's going to be like right there somewhere. Okay, so then we're going to want to work on finding the values that was going to be plotted on this curve. So first we can get the pressure values from this root that we've been using. So, because these are the vapor pressures. So that will be equal to this. And then we don't want that every time, but it'll be just our pressure guess. We'll call that for now, and we'll define what that is later. And a temperature. Alright. And then we're also going to need volume values to plot, because it's a pressure versus volume curve. So our volume values, we can find those pretty easily, because we're going to find those from, which one is it? Cubic V. So it's this one right here. So it'll return the three values to it. So we will, so we'll just have so we'll have a vapor pressure of like the liquid phase, so like the vapor of the liquid phase and the vapor of the gaseous phase. So we can call that vapor of liquid and vapor of gas. Of course, this will also output like an intermediate vapor here and somewhere in the middle, but we don't really care about that, so we're just going to use the underscore as like a trash variable. Like it'll calculate it, but we're not going to use it for anything, so it doesn't matter what we call it. And then that's just going to be cubic V of PVAP, because we're going to want to add this pressure that it calculates, and whatever temperature we use. Alright, so then we're going to want to look at the temperatures. So the thing about the temperatures is we're not going to want like linearly spaced temperatures, because we've got a logarithmic scale plot, And so we'll end up with kind of like a gap in the middle of our curve. And so one way we can do that to fix it is we're going to model our temperatures. Instead of just being linearly spaced, we're going to make them spaced like a 1 minus e to the negative x plot. So you can see right here, I've plotted that out for you so you can see the shape where we'll have just a few values at the beginning and then like a whole bunch of values right here. And so it'll be like a couple values here and then a whole bunch right here in the middle so that it will connect up and we won't have a large gap. So we'll use that, and then obviously we're going to want to raise it. We're not going to have it want to intersect at 0, intersect it a lot higher because, 0's not what we're going to want. So what we're going to do for that is we're going to have the temperature be equal to, so first we're going to have the critical temperature minus, let's say about, 275 maybe for our temperature. And then multiply that by this, so 1 minus e to the negative x, 1 minus e to the negative x. Does that need to be np dot? I don't know. We're going to do that, see if it yells at us. Because we've defined e above, so I don't want to confuse it with a variable. So hopefully that's what it means. All right, and then we'll put parentheses around his. Okay, and then we're gonna want to. Where is this? Okay. And then add the 275 back. So that's what we're gonna do for the temperature, and then we're gonna iterate through different values of x. So for x in range, let's say 0 to 7 and maybe 500 points. And then we're going to put these all inside. All right, so for each point that we have, we're going to, or for each iteration through this that we get, we're going to end up with 2 points. One on this side of the curve, one on this side of the curve. One with VL as the vapor, or the volume, sorry. The volume of the liquid, one with the volume of the vapor. The pressures will be the same for both of those. And so we're going to want to make a growing array or list. So as it iterates through, it will append a new value to the end of a list, and then we'll use that list as plotting purposes. So let's define these lists up here. So we'll call this pvap list. We're just going to make it empty for now. And then we'll have the VL, so the liquid volume list. Again, we'll make that empty. And then we'll have the gaseous volume list, which will also be empty. And then we're going to append these values on. So pvap list dot append pvap, and then I did it again. Right, and then the volume liquid list append the liquid volume, and then VG list dot append the gaseous volume. Okay, so now we'll have that. So now we need to look at what is our pressure guess. So we don't want our pressure guess to be the same every time, because our guesses will get unreasonable pretty fast. As the temperature, is increasing, this also needs to change. So we'll start with a low pressure. So our initial P guess will be maybe 100 pascals. So that's going to be pretty low. And then we're going to want our P guess to increase each time. So to do that, we're going to make our P guess the previous vapor pressure of the liquid. So it will continue to increase, so it'll just be the vapor pressure of the, temperature below it. That will be the gas for the next temperature, basically. So we'll just have, we'll update P gas at the end of every loop, and that will be P vap. All right, so next we're just gonna enter that in, make sure I don't have any typos. Oh, I have one typo there. And then, TC needs to be p.tc, so that's searching that library that I inputted earlier for the critical temperature. And then, all right. And then it didn't come up with an error, but I'm pretty sure this is actually supposed to be mp.exp, so. And then the exp will put it in the exponent anyway, so we don't need to make it an exponent. All right, so now we should be good. Sorry about the typos. So next what we want to do is, so right now we've got a list of the pressures from low to high. We've got a list of the volumes of the liquid from low to high, and we've got a list of the gaseous volumes from low to high. So right now, if we were to plot this, we'd have to plot, the liquid side separate from the vapor side. So we kind of want to combine these lists a little bit to make them, one solid curve. So let's do that. So we're going to have our pressures for plotting purposes, and that is going to be equal to, so we'll start with pvap list. So that will take us up here to the middle, and then we're going to want the pvap list again, because we're, want it for that side and want it for that side. So pvap list, but we're not going to want the list in the same order. We're going to want it in reverse order, because we're going to want to go from low to high and then from high to low. So to do that, we're going to say that we want all the rows, all the columns, but our step is going to be -1, which means that it's going to step in reverse, which will basically just flip the list around. And then we'll do something similar with the volumes. So our volumes, for plotting purposes, is going to be equal to, so we'll start with the liquid volumes. So those will be, from low to high, just like it already is. So we'll just put that in there. And then we want the gaseous volumes from high to low instead of low to high. So we're going to do something similar to the previous one, where we're going to go with the gaseous list, and we want all the rows, all the columns, but we'd want it in reversed. All right. And then, so I've made an error somewhere in here. Oh, I put commas, so you don't need commas for this. All right, so there we go. So now let's try, plotting this. So we're gonna do fig2.add scatter, and our x's are going to be our v plot, so our volumes for plotting purposes. Our y's are going to be our pressures for plotting purposes. That should be an equal sign, not an underscore. Okay. And then we can have our mode equal to lines, and then choose a color that are different on all of these. So maybe black, because white won't probably show up against the background. So let's try black. So then line color equal to black. And then we can name this curve to be Maxwell construction. We'll just call it Maxwell. Okay, let's try that. because we found the curve using, the Maxwell construction. So, see what we get. Oh, I need quotes around Maxwell. Alright, let's try that. Alright, so we probably need to zoom in a little bit. So for our x-axis, probably need a better range. So range is going to be equal to, let's see. Alright, so, I don't know, let's just try zooming in, see what happens. Alright, so you can see that that's getting us a flat line, which is not what we want. We want a curvy one, so that means I made a mistake up here somewhere. Okay, so it's when I was doing my loop, I typed range, and I meant to make linearly spaced values. So we want this to be np dot lin space. Alright, so let's enter that in to that end, and there you go. We've got our curve, just like that one. And so that is how you would plot the Maxwell construction. Or you would plot this this curve connecting the liquid vapor pressures, or the liquid volumes to the vapor volumes using the Maxwell construction.